Trying to find a rule linking the time, so linking the time with the red answer here. So how do we get in time 2? So we imagine that we got to time 10, what would the red number be? Alright, so this is kind of a just a rule for pattern spotting. So the first thing we're going to do is just going to look at the differences. Let me just get the right red pen. And so as you can see, each time you step up to the next number, you can see it's plus 7. Now you know that there is the 7 times table, right? 7 times 1, 7 times 2, 7 times 3. That would go up by 7. And so that's all we really have to do. We just have to check to see if the 7 times table can do it for us. So go ahead and try. 7 times 1 is 7. 7 times 2 is 14. 7 times 3 is 21. And now check how to get down to 2. It's subtract 5, subtract 5, subtract 5. So 7n subtract 5. Now I chose n because that's, I suppose, a traditional number to choose. N maybe for the natural numbers, right? These integer values here. But you can equally choose any letter. And as this is time in seconds, you could choose a t if you like. It doesn't really matter what you choose as long as you understand what the variable represents. And that would get me the red number. So r equals 7t minus 5. Now let's go ahead and do the same with the blue. So how do we get from 1 to 31 is the key question. But let's go ahead and have a little look at the pattern going across like this. And I think that's plus 4, right? Plus 4, plus 4. So that's something to do with the 4 times table. So let's go ahead and do that, 4t. And then you think, well, let's try it. 4 times 1 is 4. But I have to get up to 31, so that's plus 27. But let's just check it works for all of them. 2 times 4 is 8, plus 27. That seems to work. 3 times 4 is 12, plus 27. Yeah, there we go. So there's blue. Okay, so now you've got that. That's how to find the rule for each of the red and the blue number at a certain time t. But let's just go back and revisit how to get that rule again, because I'm always a big fan of just actually extending the pattern backwards. So if we know going this way is subtract 7, then when we subtract 7 more, we'll get negative 5 here. And if we go backwards here, subtracting 4, we'll get 27 here. And can you see something pretty cool? Right? So the negative 5 is here. And you can see the 27 is here. So that's a nice way of getting that starting number. And so we want to know when will the red number ever be the blue number. So we can try that. We can try an equation, right? So when will the blue ever be the same value as the red? Well, let's go and write down 7t minus 5. And let's see, equals to the blue, 4t plus 27. So is there a particular t value, right? Is there a particular t value here that will give a particular blue number, oops, and the same red number? So we want these guys to be the same. Okay, so that's what we're trying to do with setting this up. But now we have this, I'll just change to a black pen, and we're just going to do a little balancing method. Subtract 4t, subtract 4t. So that's 27 equals 3t minus 5. Let's plus 5 to both sides, plus 5. That's 32 equals to 3t. And that's interesting because t equals 32 divided by 3, which is 10.66 recurring. So that's interesting, right? It's telling us that if I have a 10.66 here, then the two numbers will be the same, red and blue. But of course, I cannot have a decimal number up here for t. It can only be integer values. So this is telling us that while we've solved the equation there, the actual numbers, red and blue, will never be the same. Okay? Let's go ahead and do the next one. I'm going to do the extra trick of fitting in the start number, if you like. So this is plus 3, plus 3, plus 3, right? Each time, plus 3, plus 3, plus 3. So therefore there will be a 1 here. This is particularly helpful, I think, for the blue. This is subtract 5, right? Minus 5, minus 5, minus 5. So therefore back up here as 105. That would be for the 0 here. And now I think I am just going to go the red one. And isn't the red one 3t plus 1? Right? And again, you can try it using the previous method from the previous question. So that would be the red. And wouldn't the blue now be equal to 105? 105. And now it's negative 5. We're going down by 5. So subtract the 5 times table. Now you can just check that, make sure it works. Let's see. Let's try t equals 4. So if we substitute 4 into here, that would be 3 4s are 12, plus 1 is 13. That seems to work. And let's substitute 4 into here. 4 into here. So that's 20. 105 minus 20 equals 85, and that works. So we found the two linear rules. Now you might like to think why we call them actually linear rules. We'll get onto that in a moment. And let's go ahead and just solve this equation then. So change to black. We're solving when does 3t plus 1 equal 105 minus 5t. So go ahead and add 5t to both sides. 8t plus 1 equals 105. And then subtract 1 from both sides. 8t equals 104. And t, when we divide both sides by 8, divide by 8, t equals 13. Okay, so we know that these two numbers will be the same when t equals 13, but we have to go and find those numbers, right? So when we've got 13 here, we substitute it into the red rule. That's 3 times 13 is 39, plus 1 is 40. So the red number will be 40. Now hopefully the blue number will also be 40. Let's go ahead and try that. 13 into here. 5 times 13, I think that's 65. And 105 minus 65 is also 40. Alright, so we've managed to find the right answer there. When t equals 13, we will have blue and red equaling the same amount, and they will flash up as 40 on the screen. But let's just pause there and let's just go to a slightly different way of looking at this. And so here we're going to go and have a look at our TI-Nspire. Now our TI-Nspire is going to give us a little bit of an extra boost here. Okay. Now if I have a little look on my, I'll go to question 3, right? So this will be time, and this will be red, and this will be blue, and time will be 1, 2, 3, 4, 5. Oh, not 5. And red, I'll just do red to start with. Red will be 4, 7, 10, 13. Now I'm going to go doc, insert a data and statistics. I'm going to put T on here. I'm going to put red here. And that's why it's called a linear model, right? A linear function, because they're going up in a straight line. And this is the, well, what was it? The 3 times table, because as you go 1 unit along, it goes 3 up. So it gains a height of 3 for each step along. This is the gradient of 3 or a rate of 3. Now we can actually get the calculator to do the straight line through here. Menu, analyze, regression, and linear mx plus b. That should be familiar to you. And voila. Y equals 3x plus 1. And you can compare with our red equals 3t plus 1. So the y represents the r value on the y-axis, and the x represents the t variable on the x-axis. So that's pretty magical, right? And now let's go back to our spreadsheet up here. We're going to put the blues in. Now that's 100, 95, 90, 85. And we'll go here. And let's go and change the r now to b. Yeah, and automatically it's updated the linear rule, so minus 5x plus 105. And that's what we've got. We've just got it written round the other way on our blue rule down there. Okay, so that's pretty good. There's one more thing we can do now on here. If you now go back to your home page, let's just open up a graph down here, And I'm going to type those rules in. Now this is f1 of x, it's functional notation. This is like the red here, r, the output, the y value, equals 3. Now we can't put t because when we draw a graph it likes to have x as the input, so 3x plus 1. So here it is, and then Control G is a shortcut for getting back to plotting another graph. I'm going to type in 105 minus 5x, not t, right? And of course we don't see the next function for the blue here because the numbers are so big. But if we go Menu, Window Zoom, Window Settings, now let's just go and choose maybe -1 to 10 for the x. And for the y, I think we've certainly got to go up to 105, right? 110 I'll go for. And there we see it, okay? Now, we really want to see where these graphs cross over. So you can see we might need to increase the x-axis a little bit. You can do it in a number of ways. You can go back the long way, Menu, Window Zoom, Window Settings, and then change the x value here, okay? And that's good. But you can also grab each label, make sure they're out of the way. Isn't it interesting that the blue and the red that's been defaulted on my TI-Nspire is the wrong way around the question we did, okay? I think we'll be okay with that one. Now you can also double click on the actual number here and you can change it manually that way. And now we can see this point seems to be interesting. Menu, Analyze Graph, Intersection. You have to click a point before and click a point afterwards, and there you go. So when t equals 13, both blue and red numbers are 40. Okay, so quick summary. In a spreadsheet, put your labels at the top here. It's very important that this top line has got a label in to define the variable. T for time, R for the red colour, B for the blue. Make sure the numbers are in. And then we go doc, insert a, next to the list and spreadsheet is their data and statistics. So it's kind of side by side. Anytime we put data into a spreadsheet, we want to plot the graph using number 7, not using number 4. So from here to here. And then when you click on the variable, you can choose which variable to go on each axis. And then finally, Menu, Analyze, Regression, Linear mx plus b, and there's your rule. And don't forget, we can go back to the home, we can put in a graph here, and automatically we can just go ahead and transfer 3x plus 1 into here, and it'll draw a nice picture. Double click on the numbers here, and we can type in manually, rescaling, right? And that's pretty useful. And then Control G, we can get another one in here, and then that's 105 minus 5x. And finally, Menu, Analyze Graph, Intersection, click, click, boom. Hope that helps.